smart computing and machine learning application. Okay, we have four presentation in this session. Every presentation may contain 10 to 15 minutes, and then we have 5 minutes for Q&A session. Okay, we will start with our first presentation. And paper ID is 20, and paper title is organizing multi-user human connection in device via deep network over audio sensor. And the presenter is Mohammed Hansla. Mohammed Hansla.
Excuse me.
Okay, Mohammed Hansla, you have 15 minutes for your presentation, and then 5 minutes for your session. Please start.
Assalamualaikum. This is Mohammed Hamza from the University of Islamabad, and today my presentation is the title of the presentation is multi-user human context while deep learning audio sensors. So starts off with the table of content. Here is the table of content that we follow. Basically, start with the introduction, and then we discuss the video, and then post over work methodologies, results, user work, and then user reference. So starts off with the introduction. Basically, connectivity initial very in nowadays, especially when we talk about wearable sensors, become challenge nowadays. So there are some problem when we capture human activities when multi participants present in a scenario. There are some serious language struggle with single user network. There are multiple misalignment issues and certain issues and So after getting all the features, we will first perform feature fusion. This will suppress all the features, and then utilizing to optimization method, which is basically inspired by Hadoop optimization technique. It will basically optimize all the features and remove the redundant irrelevant features and give us the most prominent relevant feature which is basically helpful in classification. After performing optimization, then this is very essential step in our pipeline because multiple participants doing activities, right? So if here we will show for the four participants, one person is standing. And the other person is doing some other activities. So we basically create a unifying timeline that basically demonstrate the user activities throughout the activity session. So this is the second last module of our pipeline is basically graph neural activity mapping, which is done by graph neural, where P1, P2, P3, and 4 shows the person nodes and basically Alice shows the activities among the users. So after that, the last module which is classification, in which we utilize DN neural network. It will capture all the activities which were present in this dataset. So basically, we perform on this dataset to capture 24 dataset, which is public available dataset. It's a very large size dataset which holds actually 12 participants, and it contains 12 activities, and we have done with NUCES method for the validation of our model. So here's the confusion matrix of our work, which is demonstrate the diagram. It shows the how good the model captures those activities, and here's the results of decision, recall, and effort scores, and basically this is the comparison with the previous some of the previous works that was done on this dataset. So, conclusion, we perform a hybrid technique-based model that combine multiple techniques and then come up with a new and unique model that captures the multi-user activities and dynamic environments, and creating a decent, you can say, functional accuracy on multi-participant data. And in future, we'll try to adopt some transfer-based method and diversify our scope, like in different environment, like in healthcare, in sports, or some other environments as well. So here are the few references, and that's it. Thank you. Hostel, please.
Thank you very much, Mohammed. Is there any question from the audience? Okay, I have a question.
Yes, sir.
You have mentioned over there feature fusion.
Yes, sir.
And then you have utilized quaternion information for features.
Optimization.
Yeah. Quaternion based features. You have utilized these features.
Yes, I did.
Okay, and you mentioned that are three-dimensional. But quaternion information that is dependent upon four-dimensional information. That's not a three-dimensional information. How do you manage this one?
So quaternion basically sensor data contain three-dimensional information: accelerometer, gyroscope, and magnetometer. That's why quaternion yes contain four-dimensional information, but in our case we utilize because it will capture three dimensions for us. So that's why we try to adopt this quaternion algorithm in our research.
Actually, you are talking about angles along x-axis, along y-axis, along z-axis.
Yes.
But quaternion information that's not along x-axis, y-axis, z-axis. That is four-dimensional information. I'm just talking about how you manage this one.
In depth, I have no idea, but we utilize to capture three dimension in our case because the data contain only three sensors data: accelerometer, gyroscope, and magnetometer.
Okay, thank you very much for your nice presentation as well. Thank you. Okay, we move ahead. Our next presentation paper ID, that is 40, and the paper title Multimodal for Group Activity Recognition Using Dynamic Graph Neural Network, and the presenter is Icit Zahra. Ishrat Zahra, are you available online? Ishrat Zahra, are you listening me? Ishrat Zahra, are you listening me? Ishrat Zahra, are you listening me?
Yes, I'm listening.
Ishrat Zahra, you are the next presenter. Are you listening me?
Yes, I can hear you.
तो माइक भी चल रहा है
Hello,
पीछे
am I audible?
आपको मेरी आवाज आ रही है तो आप जस्ट मैसेज कर दो वहाँ पे यू आर लिसनिंग मी.
स्पीकर नहीं चल रहा
Am I audible?
Yes, yes, you are audible now. Okay, Ms. Isha Zahra, now over to you. Please start your presentation. You have just only 15 minutes for presentation, and then we have a Q&A session for 5 minutes. Now over to you.
Yes, hello everyone. Please confirm if you can see my screen.
Ms. Isha Zahra,
Good afternoon, everyone. My name is Ishrat Zara from University-Islamabad, and the research article I'm going to present is multimodal sports group activity recognition using dynamic graph neural networks. So the agenda is we'll look into the introduction, zero motivation, applications, we'll dig into the methodology step by step, then experimental setup, we'll walk through the results, and we'll see the comparison and conclude the topic with the future work. So, what is group activity activity recognition. Group activity recognition is basically collective human behavior. You can say that there are multiple humans present in the scene, and our model will classify that with what type of group activity is happening right now. So, in this specific article, we are targeting sports. It goes beyond the individual action because in group activity, we model the group dynamics, spatial relationship, and temporal sequences. And the challenges in sports are basically the rapid movement, occlusions, and as there are multiple players, we have to model the interactions between them. So, but for this specific project, we choose volleyball because in volleyball there are complex team formations, plus there are distinct rows of multiple simultaneous players, and there are multiple occlusions seen, and the players are present with the varying skills. So, in previous methods, we see that there are most approaches either rely on visual appearance features or skeleton-based features. So, this basically where we exploit the synergy between full body features and joint-based features. Plus, the models often struggle with occlusions and dynamic player interaction, and we have the deep learning methods and web models, but they are computationally intensive methods and impractical for real-time deployment. So our goal is to design a lightweight multi-model framework that uses full-body visual features with skeleton-based pose estimation for accurate group activity detection. So where this can be applied? It can be applied in sports analytics, highlighting broadcasts for coaching and training, in abnormal crowd behavior detection, in social surveillance, and also in robotic collaborative systems. So previously, we can say that there has been some work done in the field. It starts with the RGB appearance features. Then there are models like actor relation graph, which utilizes the graph-based method. Then we have some deep learning methods like purely the transformer-based methods. But most of them either rely on the appearance or pose features. In our proposed method, we are applying appearance plus pose and also the motion features. So this is the proposed work. For the overall framework, we start with the pre-processing, then we have human detection and segmentation using YOLO-11 and GrabCut for the segmentation task. So these, we extract the silhouettes, and these silhouettes are passed to the full-body feature extractors and giant-based feature extractors. So after extracting the features, we apply the KD optimization to optimize the features and we fuse these features. And after fusion, we apply DGN and dynamic graph Google reference modeling to model the spatial temporal relationship among the players. And lastly, we have software classifier to classify the activity. So we start with the pre-processing. We have median filter and sharpening filter to pre-process the frame. Median filter basically removes the noise from the video, and sharpening filter it enhances the edges and fine details. So we get a clean, high contrast frame that improves the detection accuracy. Next, we have human detection. We apply YOLO V11 because it is quite fast, provides real time, and the output is like we get the bounding boxes with class probability for each detected pairs. So in segmentation, we remove the background of these bounding boxes and we get the clean silhouettes. We apply the GrabCut algorithm because it isolates each pair from the whole background and produces like clean binding mask for precise feature extraction. Firstly, we extract appearance features. We apply three types of appearance feature extractor. We have half histogram-oriented gradient. Then we have IDT, improved tensor trajectory, and scale invariant feature transform, SIFT, where we get the key points on the body. So in histogram-oriented gradient, it captures local gradient orientation within test silhouettes, and it is effective for distinct body postures. IDT, it captures the motion patterns, which is critical for action discrimination, like activities like spike or jumping or Next we have skeletal feature extraction. In skeletal feature extraction, we apply a media file to detect the 13 key body joints, like shoulders, elbows, wrists, ankles, and through these key points, we calculate the distance, velocity, and acceleration features. Then the next we have MOCON, in which we capture the motion related features. It is like multi-layered spatial analysis, which combines individual position with team level dynamics. So through the set key points that we calculated previously, it computes the gradient vectors. The next we have KDA, which is for feature optimization. Why we choose KDA? Because it maximizes between class variance and minimizes within class variance, and it reduces feature dimensionality by keeping the discriminative information. And in feature fusion, we fuse all these features, appearance-based features, skeletal features, and motion features, and we apply weighting coefficients which control each feature's that's contribution. So next we apply region and spatial and temporal modeling. Why we apply region in our case, we have each player as node, and edges represent the spatial and temporal interaction among the players, and we have the specific adjacency matrix which dynamically update as each player moves. So it captures both proximity, the spatial relationship, and also the action sequences over time, the temporal dynamics. So it handles evolving group formations typically present in the volleyball. Lastly, we have softmax classifier. It classifies among 8 volleyball activities, which predict the most likely group activity for each video segment. And we have 8 activity classes overall, which are mentioned: right set, right spike, right midpoint, left set, and so on. So these are the experimental details. The dataset we utilized is volleyball dataset. It is well annotated dataset, and it has like 8 group activities, 48,100 frames, and 55 video clips overall. These are the experimental outcomes. We can see the confusion matrix. This is like in right side, model performs quite well. There are minimal confusion in right pinpoint, left pass. These are the performance matrices we used. This is the RLC curve for the results. So this is the comparison. We compared our model with appearance-based methods and ball-based methods, and we can see that there are some models which perform quite well, but these models utilize transformer-based methods or purely deep learning methods, which are computationally intensive. We proposed a novel multi-model framework which combines full-body visual features and skeletal features and also the motion features. So we apply regional spatial temporal modeling for capturing player interactions, and our model achieved 90.3% classification accuracy and 88.8% mean average precision on the volleyball dataset. This offers a strong balance between recognition performance and computational efficiency. So, in future work, we can extend it to the other sports like basketball, football, handball. Plus, we can optimize it for real-time deployment on edge devices, and we can further incorporate the temporal intention mechanism. We can use file stream modeling or other temporal methods like RNN to capture the temporal dependency. We can use transformer-based architectures for richer spatial temporal representations, and transfer learning can also be applied. These are the references. Okay, we can go ahead with the questions now. Thank you.
Thank you very much, Icit, for your short and nice presentation. Is there any question from the audience? Okay, I have a question. Icit Zora, are you listening me?
Yes, yes, I'm listening.
Okay, you have mentioned in your presentation that you have utilized giant-based features as well, and there are 13 number of giants you are utilizing.
Sorry, I can't hear clearly.
13 number of giants, yeah. If giants are accumulated with each other during playing volleyball or football, then how you manage this one?
Okay, so you're trying to ask that if we apply this model on other sports, like if it's generalizable on other sports as well, if I'm getting it right.
Okay. Okay. My second question is you are utilizing median filter for smoothing and then Laplacian filter for sharpening. So why are you smoothing and then sharpening? Is there any specific reason for this one?
Well, there were like scenes that if you have seen the data set property, this is specific to the data set because there are some occlusions in the scene and quite jittered with some of the frames. So that is why I tried to plan the median full filter first and then went for the shortening filter. Some of the frames had this requirement.
Okay, thank you very much. Okay, we move to our next presentation. Paper ID is 212 and the paper title is a multi-model spatio-temporal framework for collective activity recognition. And the presenter is again, I think so, Ishrat Zohra.
Yes, it's my presentation. I will
Okay.
share the screen.
Okay, over to you.
Okay. Okay, so the next research article is multimodal spatial temporal framework for collective activity recognition. It is also a framework related to the group activity recognition, but we are utilizing a different data set in social surveillance data set, which we look into the detail. So this is the agenda. We look into the introduction, problem statement, applications. Also, we look at the variety of our work, dig into the methodology, experimental setup, results, and evaluation. We conclude conclude it with the future work. So again, group activity recognition, it involves understanding both individual action and complex interaction among multiple participants in dynamic environments such as sports, social surveillance, social scenes. Like it can be applied in almost every area of life. You can say that we can also apply in the healthcare. But specifically, the challenges we face occlusions, background clutter, the environment is changing. If we apply appearance-based method, only they struggle with the environmental variation. If we go for the skeleton-based method, they may overlook the discriminative visual cues. Transformer-based method do perform well, but they are computationally demanding. So the problem statement is most methods rely on a single modality, then the fusing strategy requires quite good attention because geometric descriptors with components is often overlooked. So objective is to design a lightweight multi-model framework which captures spatial and temporal dependencies among the individuals. Uh, The applications, again, we can apply in the novel crowd behavior detection. We can go for the sports area. We can apply in the social robotics, healthcare, and also the human-computer interaction. So modality is basically we are going for the hybrid multimodal fusion. We are integrating appearance-based features, skeletal features for comprehensive activity understanding, and adaptive spatial modeling. We are applying graph attention network for spatial modeling, and we are using BioSTM to capture both the past and future context. KD optimization is used for the feature dimensionality, and our model achieved 88.3% accuracy at approximately 20 frames per second. So, previous work has been done in the field. Again, HTTM model was proposed and it used RGB modality. Then there were some RGB plus spatial modality. But again, these models, some of the models were quite heavy, demanded heavy computation, and some of the models were lightweight, but the accuracy was quite low. So our model applied GAP plus bilateral modeling and also the multimodal RGB plus pose feature extractions. This is the overview. We have the pre-processing using histogram equalization and bilateral filtering. Next, we have segmentation. We are segmenting the scene using DPAP3. We have the human detection using mask CNN. We get the RGB silhouettes, which are passed to the full body feature extractors and joint feature extractors. In full body, we have PD features, distance transform features. We look into the detail later. Next, we have a KDA feature optimization. These optimized features are passed to spatial modeling, GAP, and temporal modeling using PyStream. Lastly, we have softmax classifier to classify the activity. So pre-processing with the bilateral filtering, it reduces the noise. Histogram equalization is good for the visibility in the dark or uneven regions. The results are clean, high contrast film. And if we look into the data set, this data set has quite like low resolution frame. So that's why we applied the histogram equalization. Next, we have segmentation human detection. So we outlined DPAP-V3 as it uses advanced spatial pyramid pooling. It looks at the larger regions and without losing resolution, we can segment the scene quite well. Next, we have human detection. It uses mask CNN. Mask CNN gives like very good results. Like it detects and segments individuals at the same time. So this pretty precise silhouettes, but we are extracting the RGB silhouettes for reliable feature extraction. So we have appearance features. For appearance-based features, we have PD, partial differential equation features, and then we apply distance transform features. Why PD? Because it captures thickness maps, orientation field, and skeletal representation of body configuration. And it is very robust to pose variation, noise, and partial occlusions. And distance transform features, it captures the object to background distance and background to object distance. You can see in the results given. It encodes both body thickness variation and also the part relationships, overall shape distribution of the body. It is like rotation invariant and skill tolerant, so that's why distance transform is a good choice for appearance-based feature extractor. In skeletal feature extraction, again we are applying media5, which captures 13 key points, key joints in particular in real time. We are getting the shoulder, elbows, wrist, and through these key body points, we capture the kinematic feature. In kinematic features, we are calculating velocity and acceleration computed via simple finite differences. This captures the speed and direction of joint movements. In post-jointed features, results are given. This captures the joint angle at elbows, knees, shoulders. 8 joint angles extracted in total. So this forms a discriminating force signature. This is again translation invariant and effective for different poses. We applying KDA, as we discussed, that it is like it maximizes the between class variance and minimizes within class variance. So it reduces dimensionality while preserving the important features. In feature fusion, we are fusing all these variance features and skeletal features, and we apply weighted concatenation, and we get a unified feature vector, which is passed to the spatial modeling. CAD spatial modeling, then we have the nodes as individual, and the interaction among them is always represented through the edges. So gap dynamically learns the strength of the interaction between individuals. Like there is no fixed adjacency matrix, and attention coefficient basically the individuals which are near to each other, they are given the more weights. The edges are basically given the more weights. This allows the model to focus on the most significant relationship or interaction for activity recognition. So for temporal modeling, we are applying bidirectional LSTM. Why bidirectional LSTM? Because it captures forward and backward sequences both. So the final representation concatenates both directions and it captures fast and future temporal context. Softmax classifier is used to classify the activity. We have like 5 activities in this case. So it gives the probability given activities and the activity with the highest confidence score is chosen. These are the experimental setup details. The dataset we are applying is using is collective activity dataset. It contains 44 video sequences, around 5,000 frames overall, and this is captured in the overall pedestrian sequence. And we have like 5 activities in total: crossing, waiting, queuing, walking, and talking. This is the Venturian matrix. The model performs well in queuing activity. There are some confusion in the waiting and crossing, and the performance matrices we are using precision recall, Admin score, mean average precision, and results are given here. This is the RSC curve for CAT dataset. Okay, so again the comparison. In deep learning methods like Conformer, Composer, and in Decompose, the accuracy is quite high because these models utilize transformer-based methods or either the deep learning models. The accuracy is high, but obviously the computational demand is quite heavy. So our model achieved 88.3% accuracy, and it is lightweight and can be implemented. So to conclude with the topic, we have proposed a multi-model hybrid framework which combines PD distance transform feature with kinematic and post-geometry skeletal features. We apply GAP for spatial relationship modeling and BiLSTM for temporal modeling. KD is used for optimization. Our model achieved 88.3% accuracy on CAD dataset, and this framework offers strong interpretability and modularity. So future work can be extended to digital force models, 3D depth integration, which incorporate depth cues for improved spatial localization. We can use a hybrid model like GAT with the transformer, which combines the attention-based transformer with GAT for long-range temporal reasoning. So this can be extended to the multi-dataset generalization in like sports scenarios, volleyball, basketball, and other fields as well. Like in the healthcare, if the datasets are given, we can also apply in the edge devices. These are the references. Thank you. We can go ahead with the questions now.
Thank you very much, Ms. Ishwar Zohra, for your presentation. Any question from the audience? Okay, I have a question for you. You have mentioned kinematic features over there, and then you are extracting the velocity and acceleration information from 2D data. How you calculate velocity and acceleration from 2D data?
Sorry, can you repeat it?
I have a question in your feature slides. You have mentioned over there kinematic features, and mentioned over there that you are extracting velocity and acceleration. So how you extracting velocity and acceleration information from 2D positional data?
I think in 2D data, we start with the position of the object over time. Like we are having the X and Y features in the 2D space, and we have hidden centroids, joint centroids, and I think the secret center is there as well. So we have specific formula which is mentioned in the article, like velocity is we get the next feature minus xt. I don't exactly remember the mathematical formulation, but yes, I think that it is computed basically through the positions of an object over time.
Okay, thank you very much. We move ahead. Our next presentation, paper ID is 236. Paper title is Multi-Perspective Cross-Attention Network for Group Activity Recognition, and the presenter is Muhammad Hamdan Azhar. Hamdan Azhar, are you listening to me?
Yes, I can hear you.
Okay, now over to you. You have just 15 minutes for presentation and then 5 minutes for Q&A session. Okay, over to you.
Okay, I will share my screen now. Can you share? Can you see my screen?
Yes.
Okay. So let me start. Okay, my paper is on group activity recognition as well, just like the previous presenter. And I will start with a brief introduction of myself. My name is Mohammed Hamdan Hassan, and I'm a recent bachelor's graduate from University-Islamabad. So my paper will be basically a deep learning architecture that is utilizing graph convolutional networks and transformer networks for group activity recognition. So for the table of contents, we will cover this in a simple way. We will start with introduction, literature review, and then I will explain my proposed architecture, its entire modules. Then we will move towards the implementation and finally the comparison of our model with the systems. Okay, so what is group activity recognition? The idea is to simply classify the interaction that is being done by multiple people in a video. It has huge applications in surveillance, sports, and even crowd behavior monitoring for safety. But the issue is that it requires understanding complex spatial and temporal interactions among the individuals. Spatial means that the interactions among individuals in the same frame, and temporal means the movement of an individual across multiple frames. So the issue is that most of the time, group level activity does not depend equally for all individuals. Sometimes only specific interactions of the individuals are important to infer the group activity. So many of the existing models have the limitations that they are utilizing interactions that are not very important for the overall activity cognition. So if we look at the literature view, early group activity cognition methods, they basically relied on image processing techniques to extract features, and they would use some deep learning model to basically aggregate them for classification. But the issue is that these approaches just simply extract the features and then they simply they try to model interactions on the classification layer. The issue is that it results in less accuracy. So with time, deep learning models, they actually incorporated multiple modalities such as RGB videos or skeleton joints or even optical flow for improved representation. So the idea was to use multiple streams for better accuracy, and it actually worked for few researchers. An example is of CERN, which is an RGB based method. It actually is able to capture spatial features very good, but the issue is that it lacks problems on modeling temporal presentations properly. The same goes with Bogarts. It's actually a skeleton-based method. It's efficient, but the issue is that you need an accurate pose estimation model, so that once you have that joints, you can give it to this architecture. But the issue is that these architectures are these architecture depends a lot on the pose estimation model. So this has resulted in a lot of research towards multimodal fusion. Okay, so the more recently, graph-based group activity recognition methods have emerged with the introduction of active relation graphs, where each person in the video is treated as a node, and then spatial and temporal interactions are modeled around the nodes. The idea is to basically extract the features using some kind of spatial temporal graph. But the issue is that many of the architectures that in this domain basically rely on predefined graphs or uniformly connected graphs, where they have some uniform graph and then they try to model the relationships. Now the issue is that this results in failing to emphasize key and visuals in the scene, which is important for many group activity application scenarios. Similarly, transformer-based methods have also become very popular, where they leverage attention mechanism to capture long-range dependencies. But the issue is that they are very computationally intensive and difficult to be deployed in real-life scenarios. So our proposed architecture is actually an architecture that uses the strengths of both graph convolution and transformer networks for better accuracy. We have two branches, one spatial and other temporal, that are used to model these retentions separately. And in each branch, we have a dynamic relation module and dot product retention module that do their own work for better feature extraction. And the output of both the branches, of both spatial and temporal branches, are then fused using a spatial to temporal cross retention mechanism. This results in better fusion as compared to other fusion mechanisms, and as a result, we have better accuracy. So we demonstrated our results on the collective activity dataset, which is a benchmark dataset for all group activity recognition. So this is the proposed architecture. So we have the input frames. We use a CNN basically to extract the features of the frames. Then we use ROI align, the region of interest align, where the focus is to extract only the features of these people, right? So we use the bounding boxes that are given in the dataset to basically extract the features of only the person instead of the entire frame. Once we have the features, we pass them into the spatial branch and temporal branch separately. Here we have the dot product retention and dynamic relation modules, and each of these outputs from these modules are then weighted using the level parameter. Then finally, we have when the output from both branches get out, we fuse them using cross retention mechanism, and finally we do some linear projection to get our classification. So the first step in our architecture is the input feature extraction. So what we do, we use a fine-tuned ResNet model to basically extract the spatial feature maps. So this is the basic equation here, where we basically we use a fine-tuned ResNet, and we basically have the frames of features of each of the frames in the video. So after that, as I previously mentioned, we use ROI line. So we have the bounding boxes from the dataset, from the benchmark dataset. So we use the bounding boxes to extract the features of these people. So once we have the features, we basically pass the features into the two branches. Now the concept we're following is of an interaction field, where we are creating a graph where graph like this, where it has rows. It has a time on the row side, and n has a number of the persons on the column side, right? So this is a target person, and these are the same person. These are other people in the same frame, while this is the same person but in different frames, right? So we have made this kind of graph for dynamic relational modeling and our dot product retention. So the idea is that we are using two modules, right? So the output of these two modules will be weighted so that we can have the important information from both the modules, and then we will basically concatenate the output of both these modules. So I will describe all these modules in detail now. So first we have a dynamic relation module. The idea of the dynamic relation module is to simply give higher importance to people who are close to our target person. So what we do, we basically use a convolution layer and it goes one by one on this entire graph. So for example, if this is the target person, our convolution layer will be somewhere like this on the spatial side and somewhere like this on the temporal side. So the thing is that the idea is to give higher importance to people who are close to our target person, and basically we will extract features from the target person to from other persons around our person to update our target person, that is target group. So that's the idea of the dynamic relation module. The dot product retention module uses the concept of transformers, where the idea is that we are not going to give higher importance to people to a person close to our target person. We are going to give higher importance to individuals who have same appearance, or who have same appearance features as our target person. So in this case, for example, if there are, let's say, two people who are walking, right, and this is our target person is also walking and the other person is also walking, so these features will have, better, this feature will have higher contribution in the final projection of this feature. So that's the idea. Now, once we have this is a basically like diagram of the dot product retention module. Right, we have these the input feature of our target person, and then we have the neighbor features, and we use these linear projections. Then we perform these calculations to finally get our output feature for this person. Now, the next thing is cross attention module. So as I showed you in the start, once we have the output for both these modules, we are going to fuse them. Right? This is a spatial branch for modeling spatial interactions. This is for temporal interactions. So once we have the output, we are going to fuse them. Now, the thing is that we can use some very simpler mechanisms for fusing, where we can simply add up, concatenate the features for both the branches, but this results in lower accuracy. So what we do, we use a cross attention mechanism. So what the cross attention mechanism is, that it actually uses the idea of transformer attention mechanism, where the spatial features are taken as query, temporal features are served as a key and value. So this results in finding which spatial features are relevant to which temporal features. So as a result, we have the output cross attention features, right? So for in the cross attention module, we are basically using multiple heads. So we are passing the spatial feature and temporal feature from the branches into the heads, and then these multiple heads are working parallelly. The output of all these heads are concatenated, and of course they're linearly projected to get the this final feature. Which of course, here if I go back, this final feature comes here, and of course it is linearly projected here, and finally we get the classification. So after the classification model, of course we have the classification layer. As I already described, we do some max pooling and some linear projection to get our classification. Now, if you move towards the implementation, we're using the collective activity dataset for it is a benchmark dataset for group activity recognition. So for experiments, it has like 4 classes, and what we do for implementation is that we train our entire architecture in 2 stages. In stage 1, we basically fine tune our CNN backbone, right? The backbone that was used to extract the features from the frame. We fine tune it, and what we do afterwards in stage 2 is that we use the fine-tuned weights of the ResNet module, and we load the stage 1 weights, and then of course we add the spatial and temporal branches, our cross-attention modules, and our entire dynamic relation and dot product retention module, and we train the entire uh, architecture in stage 2. In stage 1 we are just fine-tuning the CNN, and stage 2 we are training the entire architecture as this resulted in better accuracy. So finally, our model performance is evaluated using accuracy, confusion matrix, precision, recall, and SL scores. So for confusion matrix, we see that we have 4 classes: moving, waiting, queuing, and talking. Our model was able to classify very good queuing and talking classes, but it was facing problems in waiting and moving classes. It was mistakenly classifying waiting class for moving class. And the main issue behind that we observed was that in many of the videos in group collective activity recognition dataset, the people are moving very slowly. So it looks like the model is confusing. What model thinks that they are waiting, but they are actually moving slowly. So this results in this problem of less accuracy for these classes. So we have the precision recall reference score here. So of course the same situation here arises that we have recall less for waiting, and of course or the other overall metrics are decent. So afterwards, we do an ablation experiment. Ablation experiment point is to simply, just remove each component of our architecture and find out that which component is going to be emitting how much to the accuracy. So for that, what we do, we basically, use these five models. In the base model, we have the CNN, right? The CNN, and we basically extract the features and then linearly project the data to get the classification result. So we have 89% accuracy for that. For if you use only the spatial branch of our architecture, we have this accuracy 89.2. If you use only the temporal branch, we have the same accuracy. If you use our dynamic relation module and dot correlation module, all the branches, then of course we have this accuracy. But instead, if you use the entire model, in which we are using the cross attention model as well, with this model, if you use the entire model, then we get this accuracy 94.90. And you can see the parameters change is a bit more. Of course, 11 million parameters increase, but we still have a massive accuracy increase in our architecture. So finally, we compare our architecture with other state-of-the-art methods. We see that our architecture is actually a good accuracy with other methods, but we have less accuracy than this architecture that actually uses skeleton, RGB, and flow modalities. We are using only the RGB modalities. Of course, we have less information to use, right? This architecture using all three, so of course it has a higher advantage because it has greater accuracy than us. But still, the difference is very low. So, in conclusion, we propose a cross-collection framework where we use separate spatial and temporal branches with cross-collection fusion for proper fusion. Our branch is using dynamic relation and dot product detection modules, and of course with a learnable parameter for more descriptive fusions. So, experiments on the military ability dataset shows that we have better accuracy than most of the other state-of-the-art methods. So in the future, we will explore other modalities like optical flow or skeleton modality to enhance our temporal reasoning. So that's it. So these are the prefaces, and if I have any questions, then of course I can answer. So thank you.
Thank you very much for your nice presentation, Mr. Mohammed Hamadan. Is there any question from the audience? Okay, I have a question. You have mentioned in your presentation, in your architecture, you utilized max pooling and then utilized average pooling. Why not max pooling again? Is there any specific reason?
Okay, so the idea of the max pooling is to we have multiple features. We have features of multiple persons in one frame, right? Because there are multiple individuals in one frame. So what we do in max pooling is that we are taking the maximum features we are taking the highest value feature of all the persons, right? Because this actually results in capturing the most complementary information. So for average pooling, what we do, once we have the max pooling, we have the highest feature like in each frame. So we have the frame features, right? Let's say we have 100 frames. Now we have one frame for each, one feature for each frame. Now we want to, basically, since we are doing video classification, we want to get some one single feature for the entire video. So for that we do average pooling, so that we can basically take the average of those features, and then we have this one feature for the entire video, which we are then using for classification.
Okay, I have another question. You are working on just four classes: queuing, waiting, talking, and walking. I think so. Why only four classes? There are a number of other group activities as well.
Actually, our focus was to basically have a data set which is a much more complicated one. This is actually a much more comparative data set where it is difficult to get higher accuracy on. Uh, so for the collective data set, it has very similar activities, and also it has even problems of occlusion. So we wanted our architecture to be tested on that. So that was the main reason.
Okay, another just a comment that in your comparison table, there was a state-of-the-art approach SACRF, and they use flow features and get 95% of accuracy. But you have observed in your presentation that in case of waiting class, accuracy a little bit below. So why not you have utilized flow or movement features combined with your actual features so that your accuracy may be improved?
Okay, so currently our focus was to get an architecture that is not very computationally intensive, right? Like we can of course use flow features with that, which is something that we will do in the future. But the idea was to have an architecture that is using only one modality, one RGB modality, and then having good accuracy on that. Because you can see that the architecture that you mentioned, it has only has a slightly higher accuracy overall than us. Right. So of course this will be our future work to incorporate multiple modalities for better accuracy.
Okay, thank you very much. That was our last presentation, and thank you very much again. Mr. Mohammed Handla, you may get your certificate over here, please. आप लोग वैसे बड़े टाइम पे आए हैं। आधा घंटा पहले आए तो पहले सेशन हो गया था। हमने कहा सर थक गए होंगे, अब चलते हैं। Thank you very much.